practice problems for dealing with our KB rice box style questions. All right, so I gave you some practice problems today, and they're back here. And I'm going to need data package in order to be able to tackle these, so I'd advise you to get yours out as well. All right, so let's go ahead and read the first question, see what we got here. All right, so Nikolai was making a baking soda volcano, and it involves sodium bicarbonate. So he makes a sodium bicarbonate solution, and that has a concentration of 0.342 molar. All right. And we want to be able to answer questions like, what's the hydroxide concentration? What's the pH? What's the POH? All right. So we'll start with question A. Try and see if we can find the hydroxide ion concentration. All right. So, okay. The first thing to do is to say, okay, what happens if you put some sodium bicarbonate salt in water? Well, it's going to dissociate. It's going to create a sodium ion and a bicarbonate ion. Oops. I'm going to center that over here. Okay. Oh, throw it up. What do you think? 0 out of 10. All right, I'll use this guy instead. That's also aqueous. And that's fine. And we want to say, well, do either of these act as some sort of thing, acid or base, when they react with water? If we look on our table of acids and bases, we see over here on the right-hand side, we have a... Oh, wait, where do you live? Oh gosh, there's a bicarbonate ion here somewhere. HCO3 minus. Here we go. And so this guy is a base. And so that means when he reacts with water, it's going to steal a proton from the water. So when the HCO3 ion, the bicarbonate ion, reacts with water, it's going to steal a proton. So a proton is going to be transferred from water to bicarbonate. When that happens, we're going to form the conjugate acid of bicarbonate. So bicarbonate is here, and looks like the conjugate acid is carbonic acid, H2CO3. H2CO3. That's aqueous. All right, and when this water loses a proton, we make an OH minus. Okay. And if this was a strong base, this would 100% of the bicarbonate ions would steal protons from waters. So whatever the concentration of bicarbonate was, it'd be the same as the concentration of hydroxide. However, if we look, we see that it is not a strong base. It's in the weak base category. Only these last three are our strong bases here. Everything else acts as a weak base. So that means we're going to need a rice box. So I know the initial concentration of bicarbonate is 0.342. Our waters don't have concentrations. And in the initial condition, there aren't going to be either of these. And some number of these bicarbonates are going to dissociate, or they're going to, steal a proton and become protonated, but we're not sure how many. So the number of these we're going to reduce by x, and for every one of these that gets protonated, we're going to get one of these. So it's a 1-to-1 ratio. And also, we're going to create one hydroxide. And that means at equilibrium, we have something like this. Minus x. Okay. And so then, that means we can find our Kb expression. So our Kb expression is the concentration of our H2CO3 times our concentration of hydroxide divided by our bicarbonate ion concentration. And that's 5. But unlike, say, our Kas, we don't have a list of our Kb's. It is cataloged somewhere, but we won't be necessarily supplied with them because it's very easy to find a Kb if we're given a Ka. So if we know the Ka of the carbonic acid dissociation, Kb is related. So our Ka times our Kb is equal to Kw. And so what that means is that if we know our Ka, which we do, our Ka is 4.3 times 10 to the negative 7. That means we have 4.3 times 10 to the negative 7 times our Kb. That's equal to our Kw, which is always 10 to the power of negative 14. Provided we're at 25 degrees Celsius. And we should assume we are unless it's stated otherwise. Okay. To isolate Kb, we're going to divide both sides by 4.3 times 10 to the negative 7. Divide by 4.3 times 10 to the negative 7. And so we can find our Kb has a value. And our value is 10 to the negative 14 divided by 4.3 times 10 to the power of negative 7, which is 2.33 times 10 to the negative 8. That's our Kb. So then we can take this expression and we can say, okay, well, that means 2.33 times 10 to the negative 8, our Kb, is equal to our concentration of carbonic acid times our hydroxide concentration, divided by 0.342 minus x. Now, turns out this is going to give us a quadratic equation, so we're going to have to make an assumption. We'll assume that 0.342, take away our concentration of hydroxide, is going to be approximately equal to 0.342. Okay, so that means we can rewrite this expression as 2.33 times 10 to the negative 8, which is equal to x squared over 0.342. And that is a much simpler expression to solve for. We're going to solve for x by multiplying by 0.342, multiply by 0.342, cancels these guys out, and that leaves us with an x squared. And 2.33 times 10 to the negative 8, which is still on the calculator, times 0.342. Giving us a value of 7.95 times 10 to the negative 9. And then we're going to square root both sides. And we get 8.92 times 10 to the negative 5, and that's our x value. So let's go back to our assumption. Our assumption was that 0.342 minus x is approximately equal to this. So and now we know our value of x. We can test it. Is it true that this minus 8.92 times 10 to the negative 5 is approximately equal to 0.342? Let's test. 0.342 minus our answer, is 0.34, if I was to round it, 2. So it means our assumption was valid. Okay, so what does that tell us that we want to know? What were we trying to do in the first place? Let's go back to the question. We were asked, what is the hydroxide ion concentration? Well, turns out our hydroxide ion concentration was our x value. It was 8.92 times 10 to the negative 5. So this is our hydroxide concentration. It's equal to 8.92 times 10 to the negative 5 moles for every liter. All right. Now, the next question just asks us for the pH. We're also asked for the pH in question C. So I think it might be easier to solve for question C, given this, and then find the pH. I think we can squeeze this all into one page. So question C says our pOH. Well, we know our pOH is the same thing as our negative logarithm of our hydronium ion concentration, which is 8.92 times 10 to the negative 5. So negative log 8.92 times 10 to the power of negative 5. And we get 4.04. So our pOH is equal to 4. I'm going to call it 4.0. Round it to 2 decimals. And then it's pretty easy to find our B value. Our pH. So our pH is 14 minus our pOH. Our pH is 10.0. And then we're done. All right. So next question we'll ask is, well, what is the pH of a 0.80 molar solution of sodium phenate? And we want to know, what is the pH? All right, so we've never seen a sodium phenate compound in our course before. This is a new salt, okay? And in the last question, we started by looking at sodium carbonate and just asking, well, when we put that in water, it dissociates, right? Well, we might hypothesize that this will do the same. Because while phenate, this non-sodium part of this, is not on our common ion chart, we can find it here on our periodic table. On our Bronsted-Lowry relative strength of acids and base table. So we get this ion here. So we can assume that, without knowing anything else, this isn't an ionic solution, so it's going to dissociate. H5O is going to dissociate. It's going to create some sodium ions and some phenate ions. And it looks like that phenate is an ion that is a base. And so it's going to react with water, stealing a proton from water, and it's going to create this phenol, which is a pretty interesting compound. So we're going to take that guy, which is going to be a base, and say, okay, well, that's going to react with water, which is a liquid. And when it does, a proton is going to get transferred to our phenate and create a phenol. And as a result, a hydroxide ion. These guys are aqueous. Okay. And we need the pH. Well, we're going to need to know the concentration of our hydroxide. So we're going to see if we can piece together the expression part by part. So we'll start with the concentration of our phenate, which is the 1-to-1 ratio of the concentration of our sodium phenate. And we don't care about waters. And by now, a lot of the rice boxes we use in this unit are probably starting to seem pretty repetitive, and I hope you start to see some patterns here. And so this tells us that our Kb is equal to the concentration of our phenol over our phenate concentration. All right. And as an aside, we'll find our Kb in the same way that we did in the last question. So our Kb is going to be 10 to the power of negative 14 divided by our phenol Ka, which is 1.3 times 10 to the negative 10. So our Kb is equal to 10 to the negative 14 divided by 1.3 times 10 to the negative 10. And we get 7.69 times 10 to the negative 5. Okay. So we'll put that guy in here. 7.69 times 10 to the negative 5 is equal to, we'll just put x's in for these guys. We'll get an x squared over 0.8 minus x. And we might be able to assume that, we'll take a second to say, we'll assume that 0.8 minus x is approximately equal to 0.8. I should say 80, to be honest, because if I look at the original question, we had 8.80. So I'm actually going to go back and put it in a few places. Whatever, that's fine. All right. So that means we have a simpler expression. 7.69 times 10 to the negative 5 is equal to x squared over 0.80. And we're going to multiply both sides by 0.80. That's going to give us the square of x. That's equal to this value times 0.8, or 6.15 times 10 to the negative 5. And we still have to isolate x. We have a squared x. We're going to square root both sides. And we get 7.84 times 10 to the negative 3. And what is that? What did we find? Well, if we look back at our rice box, we found the concentration of our of the phenol acid in our solution and the concentration of our hydroxide. This is like the same thing as our concentration of our hydroxide, which is 7.84 times 10 to the negative 3 molar. All right, and if we want the pH, we can start by finding the pOH. So our POH is equal to the negative log of our hydroxide ion concentration, which is the negative log of 7.84 times 10 to the negative 3. So it'll be the negative log of our answer, which is going to be 2.1. So our POH is equal to 2.1. And our pH is equal to 14 minus that. So our pH is equal to 10.9. All right. So, pretty simple question, but lots of individual steps to be thinking about when approaching it. All right. So, let's move on and take a look at question C here. So, okay, we're going to read this carefully. So, to reduce the pH, oh, that's a misprint. To increase the pH of stomach contents as they travel down the digestive tract, the pancreas injects bicarbonate ion juice with pH of 8.9. Okay. We want to know what's the POH and the hydroxide concentration of pancreatic juice. Okay, so we know the pH. It's not that hard to find the POH. So we know our POH is equal to 14 minus our pH. So our POH is going to be 14 minus 8.9. So our POH is equal to 5.1. And from here we can find our hydroxide ion concentration, which is equal to the 10 to the power of our negative POH, which is 10 to the power of negative POH, 10 to the power of negative 5.1. .94 times 10 to the negative 6 moles per liter. That's the concentration of hydroxide. Okay. So we want to know, well, okay, that's fine. How many moles of hydroxide are present in a 15.0 ml sample of pancreatic juice? All right. So we know that we have a 0.015 liter sample. And we also know that in that sample there's a concentration of hydroxide, which is 7.94 times 10 to the negative 6 moles of OH minus for every 1 liter. The liters cancel and we find some number of moles. Oops. And we just multiply straight across and we find we get 1.19 times 10 to the negative 7 molar. Moles of OH minus, which is what we were asked. That's like 10 millionth of a mole. And now we want to know, okay, how many grams of hydroxide are present in this solution? Okay, well, that's not so bad either. Because we know the molar mass of OH minus is 16 plus 1, which is 17 grams for every 1 mole. So we can take our value here of 1.19 times 10 to the negative 7 moles OH minus, And we know there are 17 grams of OH minus for every 1 mole of hydroxide. And our moles of hydroxide cancel, so we just multiply straight across. And we get 2.02 times 10 to the negative 6 grams of hydroxide ions. Okay. The next question asks, okay, well, how many molecules of hydroxide are present at 15.0 ml sample of pancreatic juice? All right, well, if we know the number of moles, which I do, I know that 1 mole is 6.022 times 10 to the 23. So I can convert the number of moles. Oh, it's not 1.19 moles, it's 1.19 times 10 to the negative 7 moles. Hydroxide ions. It's going to be equal in concentration. That's not right what I said. Kind of zoned out there. I was thinking about... Actually, I was thinking about Liam pulling an all-nighter. My mind traveled to that for a second. I hope he doesn't do that. All right. So we know that we have 6.02 times 10 to the 23 molecules of OH minus for every 1 mole of OH minus. That's what a mole is. And so then we can multiply straight across. And I get 1.19 times 10 to the negative 7 times 6.02 times 10 to the 23. And I get 7.16 times 10 to the 16 hydroxide ions. Hydroxide molecules. Okay. So, how many more questions do we have? Do we have enough time on this video? We do. Okay. We're going to move on to question 4 here. All right, so question 4 says, well, what is the concentration of a hydrazine solution? Oh, it's a new base. We know that it has a pH of 10.5. We can assume that's from the hydrazine. And we're given a Kb expression, or value for Kb, for hydrazine, which is 1.7 times 10 to the negative 6. Huh. So I think we can infer from this question that hydrazine is a base. So that means when it acts with water, it meets water for the first time. What's going to happen? Well, it's going to suck a proton away from water, because that's what bases do. If they don't do that, they're not bases. As a result, we say we have an N2H5 plus ion. Because we're not just gaining the hydrogen, we're also gaining a positive charge. And we have a hydroxide ion as a result. Okay. And we know the pH. And we're going to see if we can get to find a concentration of hydrazine, which is what we're looking for. Concentration of hydrazine. So because we know it has an equilibrium constant at Kb, we know it's in equilibrium, which means it's not true that whatever the concentration of hydroxide is equal to the concentration of the hydrazine. It's not a 1-to-1 ratio, it's a weak base. So, if we find the concentration of hydroxide, we could probably work back and find the original concentration of hydrazine, but it's not going to be 1-to-1. So we're going to start with our pH at this stage, and that's 10.50. So that means we're going to conclude that our pOH is 14 minus 10.50, so our pOH is 3.50. We'll just do this as an aside. And so then we can say that we can find our concentration of hydroxide, because our concentration of hydroxide is always 10 to the power of the negative pOH. concentration of hydroxide is equal to 10 to the power of negative 3.50. 10 to the power of negative 3.5. And we get 3.16 times 10 to the negative 4. So our concentration of hydroxide is actually pretty high. 3.16 times 10 to the negative 4 molar. So that actually means we know the concentration of the hydroxide at equilibrium at least. So we can fill in the equilibrium box of hydroxide. 3.16 times 10 to the negative 4. And we also know that however many hydroxides are made in this exchange of a proton, the same number of these hydrazine positive ions are going to exist. Who knows what those are called? And you also know that we've started with none of these in some unknown concentration of hydrazine, which is what we're looking for. So we can reason that we added 3.16 times 10 to the negative 4 moles for every liter, and we added 3.16 times 10 to the negative 4 moles for every liter here, and lost the same number of moles here again because it's a 1-to-1 ratio. So I guess something like x minus 3.16 times 10 to the negative, oops, just 4, not 14, 4. All right. Now, we know our Kb. We're told it in the question. So if I can make a Kb expression, which is going to be our N2H5 plus hydroxide ion over N2H4, well, our Kb is going to be 1.7 times 10 to the negative 6, and that's equal to 3.16 times 10 to the negative 4 times the same thing, which is going to be squared, over x minus 3.16 times 10 to the negative 4. Okay, now, we've seen before that we have this little trick we can do algebraically. We can actually do a little switcheroo here if we have this situation. We have a variable in the bottom, we want to get it isolated. We can actually switch the numerator, the denominator of a fraction, with the opposite side of the equation, as long as we're not being added to anything over here. That's a legal move. So that actually just switches their positions. It just turns out this is a little bit easier to isolate algebraically. You can do this if you like. You don't have to. If you're comfortable with the other method we covered in our notes, that's also always fine. All right. So I'm going to simplify all that. So I'm going to square this guy. And I'm going to, that's weird. Divide it by 1.7 times 10 to the negative 6. And I get 0.0588. So x minus 3.16 times 10 to the negative 4 is equal to 0.0588. And I love not writing that in scientific notation because I got pretty sick of it after a while. All right. Now to find x, we actually have to add this amount here. And the reason I kind of like this method of doing that little switcheroo step is, well, it's a little fudgy mathematics-wise. It's definitely legitimate mathematics-wise. Just kind of like skips a step of thought. But it really does illustrate perfectly how little this affects our initial concentration. It's such a small value. And we get to really see that in action when we actually try to add 3.16 times 10 to the negative 4 to this concentration. It gives us 0.0591. And it really changes it very little. So we get our x value. It's equal to 0.0591. And that was, our question asked for a concentration of hydrazine. And I think we just found it. That's what x represented in this case. So x was the concentration of hydrazine, N2H4, which is equal to 0.0591 molar. And that's it. That's our done. We're question done. All right. So we'll do question 5. I'm going to check my text messages first because I just got one. And you gotta stay connected, you know? Alright. So what do we got here? Emily's working at a pharmacy. She needs to make a 500 milliliter lithium carbonate solution for treatment of schizophrenia. Okay. And it turns out that lithium salts, you might have heard of, are popular treatment for mood stabilizers. And so first thing we're asked is, well, how does lithium carbonate dissociate in water? So we're asked formally to do some stuff we were asked to do sort of implicitly in the last few questions. All right. So lithium carbonate. So I know I've got this Li2. CO3. Because lithium has a charge of +1, and carbonate has a charge of -2. All right. And that would be a salt. And it would dissociate into 2 lithium ions, which would be aqueous, and 1 carbonate ion, which would also be aqueous. Now, we know, what else do we know? We know that, okay, that's what we're asked. And we're asked to write the ionization reaction to demonstrate how the above base ion reacts with water molecules. So which of these is a base? Well, if we look on our Bronsted-Lowry base table, we can find a carbonate ion here. It looks like it's quite a strong base. And so looks like when it reacts with water, it's going to steal a proton. Okay, so this is our base here. So we're going to put that over here and show how it reacts with water ions. Water molecules, not water ions. Well, water is not an ion. It's going to react by donating a proton to, thank you, to carbonate, to make a bicarbonate ion and a hydroxide ion. And you may say to yourself, wait, isn't that a base too? Doesn't that also react with other water molecules in the solution to steal more protons? And the answer is yeah, it does actually. But not nearly to the same extent that carbonate does. Carbonate is so much stronger as a base that any difference these guys do is trivial. We look at the difference in strength of carbonate and bicarbonate, and then we look at their values of Ka. It looks like there's 1,000-fold difference, 10 to the power of 4 difference between 10 to the power of -7 and 10 to the power of -11. So this is 1,000 times more potent a base than bicarbonate is. So we get to ignore bicarbonate as a further base in this situation. Okay, and so that's kind of it. That's what we're done, right? Okay, so now the question asks, okay, so Emily knows that the solution that she's making can have a pH no higher than 9.8 before it starts to become strange to drink. So we need a pH no higher than 9.8. But we want to know what's the mass of lithium carbonate that Emily should weigh out. Whew. Okay, so first things first. If I see a pH, and I know I'm dealing with bases, which I am, I'm actually going to try and turn that into a pOH is equal to 14 minus our pH. So pOH is equal to 14 minus 9.8. Our pOH is equal to 5.2. We can take our pOH and make a conclusion about our hydroxide ion concentration. It's going to be equal to 10 to the power of negative pOH, which is equal to 10 to the power of negative 5.2. So our hydroxide concentration is equal to 10 to the power of negative, glare, 5.2, which is 6.3 times 10, 1 times 10 to the negative 6. hydroxide ion concentration is equal to 6.31 times 10 to the negative 6 molar. All right, that's all well and good. What are we trying to do again? We're looking for the mass of lithium carbonate. To find that out, we're going to need to know the concentration of lithium carbonate in the solution that Emily needs to make. So we need to connect the hydroxide ion concentration to the bicarbonate concentration, to the carbonate concentration. And then when we can do that, we can maybe make a conclusion with the lithium carbonate concentration. All right. So we'll start with writing out our reaction. All right, and what do we know? We know that we're looking for our carbonate ion concentration. We know our waters aren't going to participate in this situation, and we know that initially in this carbonate reaction, there won't be any of these guys. We're going to gain some, enough to get a 6.31 times 10 to the negative 6 molar concentration of hydroxide ions, which means we'd have to gain 6.31 times 10 to the negative 6. Which means we have to gain the same number of bicarbonate ions, 6.31 times 10 to the negative 6, which means we have 6.31 times 10 to the negative 6 bicarbonate ions, because it's 0 plus 6.31 times 10 to the negative 6. Which means we'll lose 6.31 times 10 to the negative 6 moles for every liter of carbonate. We'll get x minus 6.31 times 10 to the negative 6. Okay, great. So we've got a Kb expression. It's going to be equal to our bicarbonate concentration times our hydroxide concentration divided by x minus 6.31. Oh, sorry, our carbonate concentration, All right. Great, so we can plug some values in here, but we need to find our Kb. So to find our Kb, we'll find our Ka. Kb is equal to 10 to the power of negative 14 divided by our Ka value for this reaction, which we see down here. And it's going to be 5.6 times 10 to the negative 11. Of negative 14. 10 to the power of negative 14. 5.6 times 10 to the negative. Negative 1.79 times 10 to the negative 4. Kb equals 0.79 times 10 to the negative 4. That's going to be equal to, on the top of 6.31 times 10 to the negative 6 squared over x minus 6.31 times 10 to the negative 6. And we can exchange these guys, switch around their positions, just to make our calculations a little bit more straightforward. And I'm also going to square this while I'm at it, so I guess, yeah, no, I won't. So if somebody's just looking at the PDF file and they're not watching the video, they won't be super perplexed by what just happened. They can hopefully follow the thread. Let's get x minus 6.31 times 10 to the negative 6 is equal to, I'm going to crunch that big number, 6.31 times 10 to the power of negative 6 squared divided by 1.79 times 10 to the negative 4. Oops. That was stuck in the glare there, and we get 2.22 times 10 to the negative 7. All right, now we're going to add 6.31 times 10 to the negative 6. Add 6.31 times 10 to the negative 6. So we actually end up getting something non-trivial in this case. So So our X concentration, our carbonate concentration, is 6.53 times 10 to the negative 6. And that is our carbonate concentration. Okay. So this is our concentration of carbonate, which is equal to our concentration of lithium carbonate. Because if we look back, we can see that this is all going to dissociate, and it's a 1-to-1 ratio. Or at least we're assuming it's all dissociated. Otherwise, it would be very difficult to do. We'd have to think about KSPs as well as Ks and KBs and KWs, and we can get pretty confused. All right. So we know the concentration of lithium carbonate is 6.53 times 10 to the negative 6 moles for every liter. Then it's just a short few steps to find. What are we looking for again? Well, let's not forget, we're looking for the mass of lithium carbonate that Emily needs to measure out to make 500 ml solution of lithium carbonate. So to finish this off, this is 5.C continued. So if we know concentration of lithium carbonate is 6.53 times 10 to the negative 6. And we know that's a number of moles of lithium carbonate for every 1 liter. And we have, how much is she making? Well, she's making half a liter. Half of one of these. And we're going to call it 0.500 liters times 6.53 times 10 to the negative 6 moles lithium carbonate for every 1 liter, and we end up with finding out that liters cancel out. We're not quite done yet because we're asked for the number of grams, the weight. So we're going to need to multiply this by the molar mass of lithium carbonate. So we're going to need a periodic table. So what do we have here? We got 3 oxygens, carbon, and 2 lithiums. Lithium's pretty light. 2 times 6.9. We have a carbon, which is 12, plus 3 oxygens, which is 48. We have 73.8 grams for every mole. That'd be 78.3 grams of lithium carbonate for every 1 mole. Okay. Of lithium carbonate. Alright. And we can see moles of lithium carbonate cancel out, leaving us with grams of lithium carbonate. And we're just going to multiply across 0.5 times 6.53 times 10 to the negative 6 times 78.3. And we get 0.5 times 6.53 times 10 to the negative 6 times 78.3. We can find that Emily's going to weigh out 2.56 times 10 to the negative 4 grams, which, let's contextualize this. This is not a lot of grams to measure out. This is 0.000256 grams, or 0.256 milligrams of lithium carbonate for a half a liter. So how do you do this? How do you weigh out that much? Do you have a scale that weighs out to the millionth of a gram? Well, typically no. Usually what you would do is make a larger solution than you need, and then just reduce it down. Throw out the rest, because it's such a small amount we're weighing out. Okay. Well, good luck on your assignment, and let me know if you have any questions with any of these.